The polarization of light intuitively explains the core concepts of quantum mechanics. In this video we will explore these concepts and even encounter the deep reason for Heisenberg's famous uncertainty principle. Let's look at a very simple setup. Take an LCD monitor which only emits light of one color or frequency. The light emitted from such a monitor is polarized linearly, which we can test by placing a polarization filter in front of our eyes or the detector. If the filter is oriented parallel to the light's polarization, nothing happens and we can still see all the light. But once we start rotating the filter, less and less light is transmitted until we arrive at a rotation of 90 degrees and no light comes through at all. Let us introduce two axes, right and up, and call them 1, 0 and 0, 1. If instead of the filter we rotate the LCD screen, the incoming beam has polarization cosine phi sin phi, where phi measures the angle to the right-oriented axis. We call this vector phi. From experiment we then know that the intensity measured by our detector for a beam at angle phi is actually cosine phi squared times the intensity measured at angle 0. Okay, what does all this have to do with quantum mechanics? Well, Einstein received his Nobel Prize for realizing that the light beam is actually quantized, which means that it consists of millions of light quanta called photons. And because we only have light of one frequency, all these photons carry the same energy, E equals h nu. Before we start rotating again, there's a very simple but also crucial observation. The polarization state of a single photon is described by the state vector phi of unit norm. This seemingly simple fact is one of the foundational pillars of quantum mechanics and called the principle of superposition. At any point in time, the physical system, which in our case is the polarization of a photon, is described by a vector phi of unit norm. Since multiplication by -1 does not change the physical polarization, we might squeeze up to multiplication of -1 into our principle. Now we can play the same game as before. Take a polarization filter and rotate the beam. For two positions it is clear what happens. Rotated to the right, all photons are transmitted. Rotated up, all photons are blocked. But the interesting part is clearly the rotation at angle phi somewhere in between. Because the detected intensity is proportional to the number of transmitted photons per time, some photons must be transmitted, others blocked. On average, however, we must reproduce the classical cosine squared result, no matter if we wait 1 minute or 1 day in between sending two photons. But the single photon doesn't care about averages. This means that each individual photon must have a certain probability to pass the filter. In order to calculate these probabilities, we use that the intensity at a detector for a beam at angle phi is the number of transmitted photons at angle phi per time. Then, the intensity at angle 0 is the number of all photons per time, because all photons with right-oriented polarization pass the filter. And now experiments tell us that the two are related by cosine phi squared. But the probability of a photon at angle phi to pass the right-oriented filter O right is of course the number of photons at angle phi passing the filter divided by the total number of photons, which is cosine squared phi. Similarly, the probability for such a photon to be blocked is sine squared phi. Of course, the sum of all probabilities is 100% or 1. Next, let us take a look at the polarization filter. In the classical theory, a right-oriented beam is not affected at all, and its state 1, 0 remains the same. An upwards-oriented beam, on the other hand, can never make it through the filter, and its state up 0, 1 is sent to 0, 0. The filter is therefore described by the simple matrix 1, 0, 0, 0. Soon we will see that this matrix already contains all the information of the measurements and will guide us to the next cornerstone of quantum theory. For this, we first define an eigenvector of an arbitrary matrix O to be a non-zero normalized vector n such that O times vector n equals n times vector n for some number n, also called eigenvalue.
Cover the whole thinking process
let's
with
take a look at
awareness
our
at
example.
once.
The first eigenvector of O is 1, 0 with eigenvalue 1. The second eigenvector is 0, 1 with eigenvalue 0.
Try to be detached from the
We
meanings
also name these eigenvectors
of the
1
thoughts.
and 0. Going back to our experiment, there's an interesting
And just
observation.
cover the whole
All
place
our
of
detector
thought.
measures is if the arriving
However,
photon passes the
you
filter
may
or not.
experience
If we name these two
that
options
place.
1 and 0, we see that they exactly match the eigenvalues of the matrix O right. At this point, this might seem like a mere coincidence.
Cover
but if we
the
look at other
internal
experiments, we
screen
will
of
find
the
exactly
images.
the same result.
Cover the internal
This brings us to the next
loudspeakers of the
principles of quantum
talking.
mechanics. First, the measuring
And any
device, in our case the
subtle
polarization filter plus
sensations
the
or
detector, is
movements
described by a matrix.
that
And secondly,
constitute
the possible measurements are given by the eigenvalues of this matrix.
the hum, the background
But there's even more
processing.
quantum mechanics in the formalism of eigenvectors and eigenvalues. For this, let's look at the probabilities again. Passing the
And if
filter is
covering the
described by
place of
eigenvalue
thought
n equals
involves
1.
for you
Reminding ourselves that the
some
corresponding
awareness
eigenvector is
of
1, 0, we see that the probability of cosine
activity in
squared
the
phi is the
brain
square
or
of the
around
inner
the
product of
eyes
this
or
eigenvector
ears
1 with the state
or
vector
tongue or
phi,
throat
which was
include
cosine
that.
phi sine phi. In Paul Dirac's notation, this is written as 1 phi squared. The same is true for the probability of our photon in state phi to be blocked by the right-oriented filter. Being blocked means eigenvalue n equals 0, and the corresponding inner product of state 0 with phi squared is 0, 1 times cosine phi sine phi squared. This gives us the next principle, which together with the previous one is called Born's rule. The probability of measuring eigenvalue n for a system in state phi with an operator O is given by the square of the inner product of phi with the corresponding eigenstate n. With the help of a second filter, one finds that after passing the filter, the photons are actually oriented parallel to the filter. But the state describing this orientation is always the normalized eigenvector corresponding to eigenvalue 1, no matter in which direction the filter is oriented. This observation gives us the last principle. After measurement, the system is described by the normalized eigenvector corresponding to the measured eigenvalue. The monitor we have looked at so far only emits linearly polarized light, but light can also be polarized circularly or elliptically. To take such polarizations into account, we actually have to allow for complex polarization vectors. It is a good exercise to go through the whole formalism of polarization, including things like lambda half-planes and so on. Doing this, one finds the following changes to the principles. The vector spaces are now complex, and the unit vectors are not just defined up to -1, but up to a complex phase. The probabilities become mod squares, and the operators describing measurements must be Hermitian. That condition ensures that all eigenvalues, so all measurable quantities, are actually real. And this is the formalism of quantum mechanics. Any quantum system can be described by a state in a complex vector space. The measuring devices are Hermitian operators on this space, and the probability to measure one of the eigenvalues is given by Born's rule. There's one thing we've not yet taken into account, and that's the dynamics of the system. These are determined by the famous equation of Schrödinger, who was one of the founders of quantum mechanics. Or equivalently, the dynamics can also be described by Feynman's path integral approach. Finally, let's exchange two polarization filters. We take the light from
Allow your awareness to freely float
the first polarization filter at 45 degrees and the second one
between the four
From what
senses,
we know so far, we can
hearing,
say that certainly some photons
seeing,
go through the first filter, and some of these
feeling,
remaining ones certainly pass the second
which is the body, and thinking.
Now let's exchange these two filters.
When you're drawn
The
to
horizontal filter is now
sound,
first and already blocks
say to
all the
yourself,
light. The second one
hearing,
doesn't even have any effect at all.
and try to cover the
Ordering of these
entire
filters
field
affects the
of
outcome of
sound
the experiment.
simultaneously,
Mathematically, this is
and
because
stay
the operators,
with hearing
the
until
matrices which describe the filters,
you
give
have been
different
able to
outcomes
cover
depending
that
on the
field
order in
of
which we begin
hearing
by them. This
and
non-commutativity
abide
of
there
operators
for a
is
few
general feature of
seconds.
quantum mechanical systems, and it is the root
Likewise,
for Heisenberg's
when you're
famous
pulled
uncertainty
into
relation you might have heard of.
the visual field, say to yourself, seeing, and try to cover the entire field of light, the entire field of vision on all sides evenly, and abide there for a few seconds. Likewise, if you're pulled to a feeling state, pulled to the body, say feeling, and feel the whole body at once on all 6 sides. And stay there with a global contact of the whole body, not just part of it. And if you're pulled into thought, say thinking, and try to cover the whole place of thought, however the place of thought may present itself to you. And if it happens that you're pulled into more than one sense at once, for example, you may be pulled into thought and feeling at the same time, then you can use the word "and," say to yourself thought and feeling, and try to cover both fields. Or if it's 3 fields at the same time, cover all 3, or maybe even all 4. You can just say 3 or 4 like that. And evenly cover whatever combination of sense fields arises. And abide in that sense of coverage for a little while before allowing yourself to be pulled to the next pattern, the next combination. But try not to get caught in any piece of the individual fields. If you're drawn to one place in the body, try to feel the whole body, not just that one place. Now, if you find that the labeling process, saying to yourself the words hearing, seeing, feeling, and thinking gets in the way, drop the labels, but have direct awareness. And if discomfort becomes so intense in the body that it makes it difficult, feel free to move at any time, but very slowly and very mindfully. Continue to let the awareness freely float within and between these four senses. But when you're drawn to one of the sense fields or a combination of them, in addition to trying to evenly distribute your awareness over the whole field, also be aware of the presence of change and movement within that field. How things shift around, spread and collapse, vibrate. And ride on those movements and changes. Stay with the impermanence in that sense field for a little while before moving on to the next arising.